Our next speaker is Dr. Mitchell Bockmann, who is a senior geologist who completed his PhD on the early Mesoproterozoic tectonic and thermal evolution of the Eastern Gorland Craton. He did that at the University of Adelaide, and he joined the Geological Survey of South Australia in 2022. He now works as a senior geologist in the Mineral Systems and Resources teams. His talk is entitled, "Where are South Australia's Carbonatites?" We'd all like to know. So would you welcome Dr. Mitchell Bockmann?
So the question of where are South Australia's carbonatites really came about after seeing a map of Australia's carbonatite distribution and seeing that the majority of them sit outside of South Australia's borders in Western Australia and the Northern Territory. And so this is despite South Australia having many of the same favourable geological characteristics that are favourable for forming carbonatites, yet we don't seem to have those occurrences to show for it. So this study, which is part of the South Australian Critical Minerals Project, really set out to investigate some of our potential carbonatite occurrences, just to really get a better fundamental understanding of these systems here in South Australia. So starting from the top, carbonatites are igneous rocks with over 50% modal primary igneous carbonate, and we are interested in them because they are highly prospective for rare earth element and niobium mineralisation. The models for formation is still a highly contentious topic, but there are three main models. They all start in the same place with melting of carbon-bearing rocks within the mantle. The first model suggests that there is only a low degree of partial melting that occurs, so you form a primary carbonatite melt out of the mantle. The next two, you have a more whole-scale melting of this mantle rock, so you form a combination of a carbonate and silicate melt, and as that ascends into the crust, there is then the separation of the carbonate and silicate phases. So in the second model, this separation occurs by magma immiscibility, whereas in the third model, this occurs by fractional crystallisation, where the silicate phase crystallises out, leaving behind your residual carbonate, which goes on to form your carbonatite. A lot of work has also been done on where these carbonatites like to form. So generally speaking, carbonatites form along mantle-tapping structures within thick cratonic lithosphere, often associated with alkaline magmatic rocks. They also form during rifting and mantle plume events, and generally from a metasomatized mantle source. So last year, Geoscience Australia conducted a review that identified 28 carbonatites in Australia. 3 of these carbonatites were identified in South Australia at Euralia, Walloway and Ulgalima. We conducted an additional review on top of this and highlighted an additional 3 locations of carbonatite potential at Billeroo North, the Umbaratna diatreme and Mount Brady. So in this presentation, I will go through some additional data that we've collected from Walloway and Mount Brady and deliver some interpretations and some prospectivity associated with that work. Starting with Walloway, the Walloway diapir occurs about 10 kilometres north of Orroroo within the Adelaide Rift Complex. Diapirism occurred sometime between the Neoproterozoic to Cambrian, and it sits adjacent to the Euralia kimberlite field, which formed during the early Jurassic with rifting between Australia and Antarctica. There's been some previous work done on these carbonatitic rocks in the 70s and 80s, but more recently, Olympio Metals last year discovered there was a sample of over 1% total rare earth oxides and 819 ppm niobium. So this really piqued our interest, and given that there hasn't been much work done in recent times on this area, we went out there to have a look to see if we could understand these rocks a bit better. So these are the rocks in the field. We saw multiple dikes between about 1 to 2 metres wide, which were intruding along the pre-existing diapiric structures, and they were hosted within carbonate-rich sediments. So this was a question that we got immediately was, well, you've got these carbonate-rich dikes intruding into a carbonate-rich host rock. Where did the carbonate in the dikes come from? And that's obviously an important part of the carbonatite model, that it needs to be a primary igneous carbonate source. So to test that, we did some stable isotopes of carbon and oxygen on the carbonate to fingerprint that source. So on the vertical axis, we have carbon in delta 13C. On the horizontal, we have oxygen in delta 18O. The red dots represent the samples from the Walloway dikes. What you'll see is that none of that data plots within the primary igneous carbonatites field. However, what we don't see is those red dots plotting up by those orange triangles, which are the carbonate-bearing host rocks from Walloway. So this suggests that there hasn't been mixing or sequestering that crustal carbonate into these dikes, and so this sort of horizontal trend toward heavier delta 18O values in the dikes at Walloway is interpreted to be a meteoric water alteration trend, and they are actually primary igneous carbonates. And that interpretation is supported by the whole rock geochemistry, where the strontium, barium, and rare earth element compositions are consistent with other carbonatites, and likewise the rare earth element trends are also consistent with other unmineralised carbonatites elsewhere. So we've got a big tick for the geochemistry, but the petrology and mineralogy is a bit more complex here. So these are backscattered electron images taken using a scanning electron microscope. And from these, we identified a spectrum of mineralogy ranging from your characteristic kimberlite minerals all the way through to minerals that are more commonly associated with carbonatites. But what we look at, what we see when we look at the textures and the relationships between these minerals is that the kimberlite minerals have formed early, whereas the carbonatite minerals tend to form late. And this is shown by the reaction textures that form around those early kimberlite minerals as they're reacting with calcite in the matrix, and likewise with the fine-grained zirconolites and apatites, and those skeletal apatites with very irregular textures suggesting they all formed late. So petrologically, this kind of looks like a kimberlite that's on its way to becoming a carbonatite. And this hypothesis tends to get a bit of traction when you have a look at the geochemistry from the Walloway dikes and compare that to some of the other kimberlites in South Australia. So the samples from Walloway shown in red, you can see they have broadly similar geochemical trends to the other South Australian kimberlites. However, they are elevated in thorium, niobium, rare earths, strontium and phosphorus. This is pretty characteristic of carbonatites and what you would expect. But they're relatively depleted in potassium and rubidium, and that's very uncharacteristic of a carbonatite. So an interpretation that can explain these trends is that the kimberlites and the carbonatite rocks that we have at Walloway have originated from a single parent carbonated kimberlite melt. As that kimberlite has intruded, we've had separation of the silicate phase and the carbonatite phase sometime along that journey. During that separation, the potassium and the rubidium partitioned into the silicate phase, which then went on to form the carbonatites, whereas the other elements remained within the residual carbonate phase, going on to form the carbonatitic rocks we have at Walloway. So going back to those definitions that we showed at the start, we do have a rock with over 50% carbonate that has been shown to be primary magmatic carbonate, and we've proposed a formation model that's consistent with either 2 or 3 shown there. We've also demonstrated that there seems to be a very strong genetic link between the kimberlites and the carbonatites at Walloway. Right, so time for a change of scenery. Now we'll go up into some very different rocks in the northern Gawler Craton, not too far away from Coober Pedy, where we have 2 carbonatite-like prospects that occur quite close to each other in Ulgalima and Mount Brady. So the Ulgalima complex, it's an alkaline magmatic complex that hosts the Caddy prospect, and those numbers there show that there are quite wide intervals of rare earth mineralisation that have been intersected here. Now, I've written there that that due to a lack of material, we were unable to contribute more understanding to the Ulgalima complex. However, I was just talking to Greg Swain in the break, and I don't think that is the case. I think that there is some material around. So Greg's going to supply that, and I think that we're going to do some work on Ulgalima, which will be really good. So I'll say watch this space. But for the meantime, I would highly recommend watching Greg's presentation from SAMEC last year, in 2022, where he proposed a carbonatite model for the Ulgalima intrusive complex. So we didn't look at Ulgalima, but we did move to another very carbonatite-like prospect not too far away at Mount Brady. So Mount Brady is adjacent to a crustal scale structure in the Karari shear zone. It's a complex of magnetic highs with both normal and reversely magnetised bodies, which is shown in the analytical signal image in the bottom right. And it sits beneath about 50 to 70 metres of cover, which is very similar to the depth at Ulgalima. Best assays here are about 0.9% copper, 2% phosphorus, and around about 1,000 ppm rare earth elements, so not as enriched as what we see at Ulgalima. However, still some level of enrichment and worth investigation. And this has previously been interpreted as a magnetite skarn related to the Hillsborough Suite intrusives. These are the rocks at Mount Brady. They're pretty spectacular. So we have these massive apatite, diopside and magnetite crystals all growing within calcite. We have these large sections of olivine and serpentine after olivine also growing in calcite. And on the calcite margins, we see these phlogopite zones, which can be up to multiple metres wide. And they tend to grade out into magnetite with these disseminations of apatite, which is the orange mineral. And in some places, this apatite is intergrown with sulfides, such as pyrite and chalcopyrite within the magnetite. So there's a lot of carbonate in this prospect, and these rocks and minerals wouldn't look out of place in a carbonatite complex. So we did some geochronology on these samples because at the University of Adelaide, they've done a lot to develop some new methodologies recently, which allows us to date a number of these phases directly. So using these new methods, we're able to date the calcite, phlogopite, and apatite directly. And these came back with some very interesting ages. I won't go through these interpretations too much today, and this is still preliminary data, but we have ages between 1580, 1500 and 1460 MA. But all of these ages do line up with known events that have been either known for a long time or very recently established in the Northern Gawler Craton. So it seems like the more work we're doing in the Northern Gawler, the more we're learning. But the one age I do want to draw your attention to, which is very interesting, is the apatite lutetium hafnium age. Lutetium hafnium is meant to capture the primary crystallisation age of apatite. And this came back at 1460, which aligns with the age of copper mineralisation at the Cairn Hill mine. And we have a very similar relationship between the copper sulfides and apatite at Mount Brady that suggests that this event could be much larger than what is currently known. Similar to Walloway, we also had a look at the composition of the carbonates at Mount Brady, but this is a very different story. We have a very large overlap with the crustal carbonates fields, which suggests that they're probably crustally derived. And that's also supported by the whole rock geochemistry, where strontium, barium and rare earth elements plot in the dominantly non-carbonatite fields. And likewise, the rare earth element trends are also not consistent with what you would expect to see in non-mineralised carbonatites. So the conclusions for Mount Brady is that the carbonates probably crustally derived, and so the previous interpretation of a skarn model is consistent. But these younger ages and their possible association with copper mineralisation is very interesting. So just to wrap up the presentation, I wanted to take it back to the start and address that question: where are South Australia's carbonatites? We've had a look at Walloway and the work that Olympio Metals have done there. They have established that there is some level of rare earth element and niobium mineralisation present. We've also established that there seems to be a strong genetic link between the kimberlites and the carbonatites at this location, and so I think that the other South Australian kimberlite fields are potentially prospective for other carbonatites. Next, we have the Northern Gawler Craton, where Mount Brady did not come back as a carbonatite. However, I think there is genuine carbonatite-related rare earth element potential at the Ulgalima complex, and hopefully we're going to find out more about that. But I think that there is broader prospectivity across the Northern Gawler Craton in general, and possibly associated with this new 1460 event. So we know at 1460 MA that we have rifting between Proterozoic Australia and North America at that time during the breakup of the supercontinent Nuna. So we have an extensional tectonic event, and we also have the presence of multiple mantle tapping structures. So I think this is a good environment where we could be potentially forming carbonatites. Third, we have the Billeroo North Alkaline Magmatic Complex, which sits in the southern Curnamona. There is a very strong association between alkaline magmatic rocks and carbonatites, and this one is heavily underexplored with only 2 drill holes. So there is a Mesojournal article on that if anyone else is interested. And lastly, to the north of the Curnamona province, there is also the Umberatna diatreme that has been published on as a carbonatitic diatreme, also associated with alkaline igneous rocks. So I think there's still a lot of potential out there. We just have to have a look at some more rocks to find these carbonatites. Thank you.